Hello, calculus class. We're going to go over section 5.5, which is integration with u substitution. So this section, you just have to be kind of clever with it. It's not easy, but it is doable, okay? So we're going to use substitution to change an integral you can't integrate into a simpler integral you can integrate. So this is the process, and this technique may help integrate some products, quotients, and compositions. So these are the types of problems that we would use substitution on. So the substitution method says, given an indefinite integral of the form, the integration of the function g of x times the derivative of g of x dx. So what we're going to do is we're going to let u equal g of x, and then we're going to compute du, which has to equal the derivative of g of x dx. Once we get that done, then we can let the integral equal the function at u du. And then we're just going to integrate. And then finally, once we do that, we're going to resubstitute back in whatever u equaled. So this is called the Swiv process. Swiv, S-W-I-V. S stands for substitution. You have to come up with the substitution. So you're going to use, we're going to choose u to equal g of x. We're going to compute the differential. So du equals g prime of x. So we're going to take the derivative of g of x, whatever that is. And here's a note, and it's very important. Your choice of u and du must be able to replace all x's and dx in the original integral, meaning that you can't be short any x's or have any extra x's left over. The only thing you can do is multiply the differential by a constant, and this is important too. You can just multiply the differential by a constant to make it match the leftovers from the original integral. If the substitution doesn't work, you're going to have to try a different substitution for u. So that's step one. So step one, let u equal g of x, take the derivative of g of x, let that equal du, and then make sure that the leftovers match, okay? The next step is to write. We're going to write the original integration in terms of u by using substitution from the previous steps. We're going to integrate the new integral with respect to the new variable u. So the integration of the function at u du equals f at u plus c. Okay? So once you get to that point where you integrated, your last step is to back substitute. So whatever u is, you're going to replace that back into the original function, and don't forget the plus c. Okay, so let's go ahead and see how this works. We're going to do an example here. So this is example 1 using the Swiv method for u substitution. Find the following indefinite integral. The first thing I'm going to do is I'm going to rewrite this, and I'm going to rewrite it so it says x squared plus 1 to the 4th power 2x dx. Okay, so I'm going to tack on that 2x by the dx. Now I can't integrate this because it's a product. So, and it's not a product that is familiar to us. So what I'm going to do is I'm going to let u equal x squared plus 1. So the reason why I picked that is because I can take the integral of u to the 4th very easily. So let's see what happens. So let's see if I did the right substitution. So if I find du, I have to take the integration of 2x plus 1. The integration, or excuse me, the derivative of x squared plus 1 is going to be 2x. Okay? So the million-dollar question, does this, and I can't forget to put dx there, but does 2x dx match the leftovers in my problem? And the answer is yes. So I did the substitution correctly, so I can go ahead and be confident in that. Now the next step is to rewrite in terms of u. So remember, I let x squared plus 1 equal u, so I have integration of u to the 4th, and now I have to have the integral match, or the derivative match. So I'm going to put du here, because remember, du equals 2x dx. Okay? So once I did substitution, I wrote it again, I have to integrate this Okay, so the integration of u to the fourth, remember we take and add 1 to the value of the power, and then whatever that value is goes in the denominator. So this is u to the fifth plus over 5 plus c, right? Or I can write this out as 1/5 u to the fifth plus c. And the next thing we have to do is back substitution. Remember, u equals x squared plus 1. So wherever I see u, I'm going to plug in x squared plus 1 and raise this to the fifth power and then plus c. So once again, in blue is your substitution, and this is my answer. So this allowed me to be able to do a problem like this, a quotient, or actually it was a product from the very beginning. So it's kind of nice. All right, let's see another one in action. All right, so we have the integration of the square root of 3x plus 1 dx. Once again, we don't have anything that matches up with that we can integrate easily. So what we're going to do is we're going to rewrite this. First of all, I'm going to rewrite this as 3x plus 1 raised to the 1/2 power dx. And I'm going to use substitution. So usually we use substitution for anything inside the parentheses or a power. So if I look at this, I'm going to let u equal 3x plus 1. Okay, so once again, remember you have to take the derivative of u of both sides actually. So I take the derivative of u, it's du, and if I take the derivative of 3x, it's 3 dx. So does that match my leftover? Remember my leftover is 1 du, or 1 dx rather. And we can see it doesn't. But what we can do is we can multiply by a constant to make a match up. So if I want this to look like 1 dx, I got to get rid of the 3, so I take the reciprocal of it. So if I multiply both sides by 1/3, that allows me to attack the 3, and it gets rid of it. So now I have 1/3 du equals dx, okay, which is 1 dx. Now this equals my leftover. So these two are now the same. So I'm ready to. So my next step, since I figured out du and I also figured out the substitution, is to rewrite. So I'm going to integrate u to the 1/2 power, and then it's going to be times 1/3 du. Okay? I'm going to take the 1/3 out. I'm going to go ahead and put that in front of the integration. So we're going to integrate u to the 1/2 du. Okay? So now I'm ready to do the integration. So it's going to be 1/3 times. Remember, you have to add 1 to the power, and then it's going to be over, and if I add 1/2 plus 1, it's going to equal 3/2. It's going to be over 3/2. And then I can't forget plus c. So let's make this look a little bit better. So 1/3 times 2/3 u to the 3/2. So this equals 2/9 u to the 3/2 plus c. Okay, so I got one more step. Don't forget to back substitute. So remember we said u equals 3x plus 1. So I back substitute that in. So my answer is going to be 2/9 3x plus 1 raised to the 3/2 power plus c. Okay? All right, so once again, Swiv. Don't forget back substitute. The next example is example 2. I'm looking at this original integration, and it's a problem because it's a quotient, and it doesn't match anything that we have. So we know we have to use u substitution. So the first thing I'm going to do is rewrite this as a product. So if I rewrite this as a product, I get 8x times 2x squared plus 1 raised to the negative 5th power dx. Okay, so first step is to substitute, let u equal whatever's in the parentheses, which is 2x squared plus 1. Du equals 4x dx. That does not match my leftovers, because if I rewrite the original problem here, as, sorry about this, it's going back and forth, 2x squared plus 1 to the negative fifth times 8x dx. That doesn't match. But I can make it match if I multiply by a constant. So I want 4x to look like 8x, so I'm going to multiply both sides by 2. So I get 2 du equals 2 times 4x dx. So 2 du equals 8x dx. Okay? All right, now these match up. So my leftovers match up. So what I'm going to do is I'm going to rewrite this. And I'm going to write this as the integration of u to the negative fifth power times 2 du. Okay? So once again, I'm going to take the 2 and place it outside the parentheses, or outside the integration sign. And I have u to the negative fifth du. Okay? Now it's time to integrate it. So this becomes 2 times, and u to the negative fifth, let's look at that. So remember, I have u to the negative fifth plus 1, and it's going to be over that same value. So negative 5 plus 1 is a negative 4, right? So let's write this out as 2 over negative 4, u to the negative fourth power, right, plus c. Reducing this down again, we get negative 1/2 u to the negative fourth plus c. Okay? Now we do back substitution. So remember, u equals 2x squared plus 1. So wherever I see u, I'm going to plug that in, 2x squared plus 1 to the negative fourth power plus c. So this is my answer. Okay? All right, so let's do one more, and then we'll have a second video. So this says integration of x squared secant squared of x to the third power du. Okay, so I'm going to make a guess here to do the substitution, and I'm going to say let's let u equal x cubed. Okay, so if I go that route, remember that du is going to equal 2x squared dx. Okay, so if I look at my original integration and I just rearrange it, this is my leftovers here, x squared dx. Does 2x squared dx look like that? And hopefully you said no, but the good news is I can multiply by a constant. So I'm going to multiply both sides by the value of 2. Or actually, sorry, I'm going to multiply by 1/2 because I need the reciprocal to make that 2 go away. So if I multiply both sides by 1/2, I get 1/2 du equals x squared dx. Okay? And now my leftovers match. Okay? So I can use the substitution and to rewrite the original equation. So we're going to integrate secant squared u, and then x squared dx becomes 1/2 du. Okay? I'm going to take and bring the 1/2 out, and then my next step is to integrate secant squared u du. Okay, so let's go ahead and do that. If I integrate it, remember that secant squared u is tangent u plus c, and now all I have to do is back substitution. Okay, so remember that u equals x cubed, so I get 1/2 tangent of x cubed plus c. So this is my answer. Okay, so that'll be it for part 1. We're going to do part 2 in a minute.